Yeah. Welcome everyone. Today we are very happy to have Lionor Kehrberger from the Max-Planck Institute for Math and Sciences in Leipzig. He's going to give us a math GR colloquium on, he's going to break all our conceptions about null infinity, why null infinity is not smooth and how to measure it. Take it away.
All right, thank you, for the introduction, and thanks a lot for the invitation. It's really nice to be able to speak here, and I'm much looking forward to any potential comments or questions that you may have. So this talk will be based partially on a series of papers called The Case Against Smooth Null Infinity 1 to 5, and also partially on joint work with Dejan Gajic and Istvan Kadar. The work with Hamid Masoud is the 5th paper in the series. Okay, so this talk will be about mathematical results concerning the asymptotics of gravitational radiation, in particular going from past to future null infinity, but also about other regions. And I'll begin by giving general background and motivation for why I'm studying this. And I'll formulate the actual problems that I'm interested in. And then I'll give you a little spoiler about what the results are roughly going to be, and explain the second part of the title of my talk, namely how to measure the non-smoothness of null infinity. So I'll explain to you why all these things have consequences on late time tails, which you can in principle measure. I'm hearing a small echo from my laptop. Should I just mute?
We don't hear it.
Okay. Okay, and then in the second half of the talk, so this will basically be most of the relevant stuff. And then in the second half of the talk, I will describe to you the actual mathematical results and the proof ideas. So this will be the more technical part of the talk. Okay, so let's begin with some background and motivation. So these first few slides, you're probably all very familiar with them, but I just want to be very clear about the setup. I'm always studying 3 + 1 dimensional classical general relativity with some matter fields. If you're curious about what happens in other dimensions, you can ask me at the end of the talk. There are things to be said about them, but I didn't include them in this talk. And most of the mathematical part of this talk will actually be about the Einstein vacuum equations.
But by 3 + 1, do you just mean globally hyperbolic, or?
No, I mean the number of dimensions.
No. So you're okay. You're not. That's no assumption about.
No.
Okay.
Just 4-dimensional spacetime. Okay, and most of this talk will be about the Einstein vacuum equations, and I here just want to emphasize the historically surprising point that GR has a highly non-trivial vacuum, which is something that we'll come back to quite soon. Okay, and now, I'll draw a Penrose diagram of the Minkowski spacetime. So, I won't work much with the Minkowski spacetime, but I'll often work with double null coordinates, which are like the Minkowski in U = T - R and B = T + R.
By vacuum, you mean?
I mean
solution, not
I mean
zero energy, just.
I mean solutions to this
T mu = 0.
Okay, so here's the Penrose diagram of the Minkowski spacetime, and I'll often work with these double null coordinates, U and V, and these are the two null infinities of the Minkowski spacetime, as you probably all know, and they are the name givers of this talk, past null infinity and future null infinity. So I want to say a little bit of stuff on the wave equation on the Minkowski spacetime, because it's a little bit instructive for the rest of the talk, even though I'm sure that most of you are also familiar with it. So the wave equation, if we look at it in spherical polar coordinates, it takes this form, and it's actually much nicer to write the equation in terms of r times v, r being the radius. And then this equation actually, what you can prove is that this equation satisfies the strong-Huygens principle, which says that the solution flows along the light cones. In particular, if we have compactly supported data like this, then after a finite retarded time, the solution will be exactly 0. This is something specific to even space-time dimensions. And the reason I'm mentioning this is because there is a quite neat proof of this. So in fact, if you project your solution to fixed spherical harmonics of spherical number L and commute with the vector field r squared dv L times, then you get an exact conservation law. And then you see that the solution really, just certain derivatives of the solution are constant in integration. and U and V. So this is one proof of strong Huygens principle. And these exact conservation laws is something that I'll exploit quite heavily in a perturbed setting at later parts in the talk, which is why I mentioned them once. Okay, and just to be very transparent about the setting here, I always regard relativity as a dynamical theory, because the Einstein vacuum equations are a system of quasi-linear wave equations for the metric components in a suitable gauge, with initial data given by some Riemannian manifold together with a symmetric two tensor satisfying the constraints. And then there is this fundamental theorem of GR that for suitably regular initial data solving the constraints, there exists a unique maximal globally hyperbolic development that you can associate to these data.
Just a curiosity, so where does the compact support condition go in that proof of Huygens theorem?
Oh, no. Huygens principle is just the statement that the fundamental solution moves along. In particular, it implies that if you have compact supported data, that the solution will be identically zero after finite time. Okay.
I got a little confused. How does the energy, how to translate the energy statement to the Huygens principle statement?
Okay, so the energy, you mean, so for the wave equation, you have a conserved energy, which is the L2 norm of the first derivative. And this is easier to see in this second picture. So the energy is something that doesn't decay because it goes to space like infinity. So particular at the end, I mean, to each of these, and if you wanted to see energy decay, you would have to measure energy along hyperboloidal slices that extend towards Hushang, because then you would see that radiation disperses along like that. But you wouldn't see decay if you measure with the conserved quantity along space. Okay, so within this dynamical formulation of relativity, an example problem that one may study is the stability of the Minkowski spacetime. This is simply the problem where you take the Minkowski initial data, this is just Euclidean space, and you now slightly perturb it so that you still solve the constraint equations and you ask what happens to the evolutions of these perturbations. And then, as was proved by Crucible and Kleinemann in 1993, these evolutions remain globally close and asymptotically settle back down to the Minkowski spacetime. I highlighted here that in their theorem, they of course made an assumption on the asymptotic decay of the initial data towards space like infinity. Maybe just keep that in mind. This is something that I'll come back to quite soon.
This may not be true if you include quantum mechanics, right?
It may not be true.
Yeah.
But this is completely beyond the scope of this talk.
Right, because the vacuum itself may be active in that case if it's not classical.
Yeah, I mean, it depends how exactly you want to define perturbations. But yeah.
So what exactly did Puhat prove that, it sounds like she didn't prove it exists they didn't prove it exists forever, right?
No, they didn't. They just proved that there is a unique maximal solution without saying how long this maximal solution lives.
Right, so it might get a singularity in a finite time.
Yeah, but there is a unique
That's
maximal
what
solution.
I see, that's
Yeah.
maximal means.
I mean, it's like with ODEs. If you have an ODE, you can prove that there exists a solution, but there exists, of course, infinitely many solutions. Like, let's say you know that the solution exists up until time equals 10, then you also know that a different solution exists up until time equals 5. So these two solutions are different, but there is a unique maximal solution. This is the same statement here, but of course in VR it's much more complicated because you're comparing manifolds. You need to be more careful with how you define maximality.
Okay.
And okay, I just want to use this slide here to just mention that Yvonne Kehrberger just died 27 days ago at the age of 101 years, and I just want to honor her immense accomplishments to the field here. Okay, so this was the very basics, and now I want to explain in more detail the kinds of conceptual problems that I'm interested in this talk. So let's say you want to describe some astrophysical process in isolation, viewing GR as a dynamical theory, starting from characteristic or say hyperboloidal initial data. Then in particular, the task of modeling an isolated matter system requires modeling the vacuum around that matter system. In particular, you have to make a choice for how the gravitational radiation around a matter looks like. And so when you have this dynamical problem and want to pose initial data, you need to make an ad hoc assumption on, in particular, the asymptotic behavior of the gravitational radiation along your initial data, which in turn captures information about the past of the system. So think of, we freeze time and we look at Sun and Earth, and we have some gravitational radiation at our frozen time. This gravitational radiation has been generated by Sun and Earth, their motion a little bit earlier. So whenever we have our initial data, then they really contain information about the past of the system. And so historically, people have always made some ad hoc assumptions on what the gravitational radiation should asymptote to. And I'll present some of the main ad hoc assumptions here. So the first one, the title giver of this talk, is the assumption of a smooth non-infinity due to Penrose. Goes by many different names: asymptotic simplicity, the Sachs-Spinning property, regular Bondi coordinates, and it's the idea that you can smoothly attach to the spacetime a conformal boundary. But I don't want to talk so much about the origin of this assumption. I just want to say what it exactly states. And it states that our initial data, the gravitational radiation, that is smooth with respect to the variable 1 over r, where r is something like the area radius, where psi4 and psi0 are the two extremal components of the Weyl curvature tensor. So here, L is the outgoing null vector field, n is the ingoing vector field, and M is a spherical vector field. And the peeling property demands that actually r psi4 goes like 1 plus 1 over r and so on. And the weighted quantity r to the 5 psi0 goes like 1 plus 1 over r and so on. This is the little hierarchy in the Weyl curvature tensor that was discovered by Sachs. Okay, this is a completely ad hoc assumption, but it does have some motivation historically. And the motivation is that Sachs and collaborators were hoping that these assumptions would describe spacetimes that would arise dynamically from the infinite spacetimes from the infinite past, where there would be no radiation coming into the spacetime from past non-infinity. And here's a little spoiler. This motivation breaks down if you go away from linear theory around the Minkowski spacetime. So this is why I'm saying non-infinity is not smooth. Okay, that's the first assumption here. The second assumption is, instead of bothering with the precise asymptotics towards future infinity, you might as well just say, well, I have no asymptotics towards future infinity because my data are compactly supported. And this you could then justify by thinking of your system that generated the gravitational radiation only having become stationary at some finite retarded time. So it was stationary up for an infinite time and then for some random reason become radiating. Yeah.
Wouldn't this compactly supported data, like at some later finite time, just give 0 by the strong Huygens?
Oh, this is a good point. So I'm now talking about general relativity. Strong Huygens principle holds exclusively for linear waves on Minkowski, and the nonlinearities break Strong Huygens principle. Okay, so if you assume that the spacetime has been passed stationary, then it's reasonable to say that gravitational radiation on your initial data slice is compactly supported. But it's maybe not so physically satisfying to just say, well, there was a random time in space-time, a random event in space-time where my matter has started becoming dynamical. This assumption is strictly stronger than peeling, of course, because here you have 0 for peeling, you just have some expansions. So this, in particular, these expansions with 0 coefficients. Okay, and then now there are many other ad hoc assumptions that can replace initial data. For instance, in the proof of the stability of the Minkowski space by Krustalon and Kleinerman, they assumed that the initial metric looks like 1 plus 2m over r times the Euclidean metric plus correction terms of order r to the -3/2. Right, just another completely ad hoc assumption on the asymptotic behavior of gravitational radiation.
With respect to your previous assumption, we know about the Big Bang. There was no history before that.
Yeah.
So does that satisfy what you were talking about in the sense that nothing can extend back in time infinitely?
I'll come back to that in 5 slides.
Okay.
I promise I have a slide on that. Okay, so just another ad hoc assumption. Ultimately, our initial data assumptions will always secretly contain information about previous states of the system. So if we want to really have precise physical control over the assumptions that we place on our data, the right thing to do is to go all the way back post scattering data in the infinite past. And I'll come back to your point in a little bit. So in order to illustrate now precisely what I mean here, I decided to just formulate two problems, which in principle I could formulate as one problem, but I think it's slightly cleaner to formulate them as two. So, and I formulate this problem in the context of an astrophysical n-body scattering. So I'm thinking of n infalling masses coming from the infinite past and coming towards each other. So the first problem is the generation of gravitational radiation in such a scattering event. So the task is to find a suitable matter model describing n star-like mass distributions approaching each other from infinitely far away, from past time like infinity, and then solve the arising scattering problem for the Einstein matter field equations in the infinite past up to some null cone, so up to some bounded advanced time v. And then I want to find what are the asymptotics towards past and infinity along this null cone. So I want to evolve these matter and see what the trace of the radiation that they emit looks like on this null cone. This problem, I think, it will be a very nice problem to solve that mathematically, but that's not been done yet, and it's not the focus of this talk. Maybe it's going to be done in 10 years, but it's already been treated heuristically in the context of post-Newtonian theory by work by Walker and Will. So, and they find, and I'll explain this argument in slightly more detail later on, that, okay, if the masses move further and further away from each other, Newtonian theory becomes a good description of their movement. If they asymptote to hyperbolic Keplerian orbits, then they find that the curvature component C0 will decay like r⁻³ here, and the curvature component C4 will decay like r⁻4 here, as u tends to -infinity. In the case of asymptotically parabolic orbits, so eccentricity 1, this is all Keplerian language now, they find that both C0 and C4 should decay like r⁻11⁻3. Okay. So this is a suggestion of what you might expect when you actually solve this problem. Now that you know the decay rates along this null cone, you may then solve the vacuum problem. So you're outside of the support of the matter, and you may then ask, how will gravitational radiation propagate from this null cone all the way to fusional infinity? So the problem is to formulate a scattering problem for the Einstein vacuum equations with data on this null cone and on past and infinity, where the choice of the data on the null cone is informed by some hypothetic n-body scattering in the infinite past. And then we want to solve this very scattering problem and find the asymptotics towards fusional infinity, towards space-like infinity. And then in particular, we have a prediction on what kinds of asymptotics should be assumed if you want to work with an initial data setting. You had a question?
So you don't assume peeling or anything that's
No.
online.
It's a good point that you mentioned this. So peeling, for those of you who know, in the past it's reversed. In the past, C0 is required to decay like r⁻1 at least, and C4 is required to decay like r⁻5. This already breaks peeling in the past. But you might still hope that peeling holds in the future.
What it means by no incoming radiation, or that's the one that you'll be made precise later.
Can you repeat the question?
What it means by scribe minus here.
So you can always still make sense as future infinity as the limiting points of null rays without specifying anything about the conformal extendability of the method.
Okay.
But like I said, this problem is not genuinely solved. So post-Newtonian theory in particular operates on a fixed Minkowskian background, and then you know that there will be deviation from the mass, the light cones will diverge logarithmically. Just keeping these assumptions there, just say there is some work on this. Well, eventually there will be more work on this. But so this is the propagation problem, and this is where we'll tell you most of the mathematics. And I will give you a spoiler now what to expect here. And what to expect is the following, that towards future infinity, you will obtain the following decay rates, which indeed both have already been predicted by Thibaut Damour and Dimitrios Christodoulou. In the case of hyperbolic orbits in the infinite past, you will obtain that psi0 goes like r to the -4, again violating peeling, because peeling would have it that psi0 goes like r to the -5. And in the case of parabolic orbits, you are 2/3 faster. So parabolic orbits are always 2/3 faster. I'll tell you in a little bit why. Okay, but these are the two open problems that I want to discuss in this talk. This is where I will present you almost the mathematical resolution, and the other one not so much.
Your C0 was gonna go like r to the -1, right?
Yeah, it would be enough that C0 went like r to the -1.
So this isn't violent.
It just turns out that the first two coefficients of C0 vanish.
Right, but this isn't violating peeling, so did you mean some other coefficient?
Oh, no, sorry. This is towards future infinity. Sorry,
Oh, so
I
it's
wanted to
okay
previous-
at future,
Towards future infinity, C0 will decay like r to the -5.
right,
Peeling holds.
in the past. it-
Towards past infinity, it's C4. So both are violated.
Okay,
Historically,
oh, this turns out, okay.
historically, people always thought that peeling fails in the past and holds in the future.
Hmm.
But I don't want to give too much
This is
attention
equally
to this.
bad in the past and futures.
I mean, there's just a lot of confusion, but of course, I don't want to repeat the confusion.
Does peeling also say that you're only allowed integer powers of 1/r?
Exactly, yeah.
Okay.
Because it says that you're regular in 1/r. And if you look at 1/r to the 3/2, that's like x to the 3/2, if x is 1/r, and that's not 2 times differentiable.
So even if like r, it's r to the -5, this like third power will also find.
It's not regular. Regularity really means you can tailor it, like, but close to 0, these become irregular factors.
Sometimes the coefficients that come along with these 1/r expansions, C0 and stuff, they give you conserved quantities, right? Newman-Penrose. So what happens to those kind of conserved quantities if peeling is violated? They're just not
They become
there.
stronger. So I'll mention that when I write on the theorem. Like,
Okay.
the two things that I'll mention. Okay, and now mostly so far I gave you the conceptual reasons why one should care about these problems. So just to epistemologically know what we're doing when we post an assumption on initial data. And I really want to say these asymptotics, assumptions and asymptotics of radiation, they're ubiquitous. If you look at any GR textbook, look at how is the black hole defined, what is defined as the complement of the causal path of non-infinity, how is non-infinity defined, what's defined by a Penrose smooth conformed compactification, and that in turn assumes asymptotic behavior of gravitational radiation. So just epistemologically, these things are everywhere. But okay, some of you might say I don't care so much about epistemology. And for those of you, I have this little section, consequences on late time tails, where I'm claiming that some of these things might actually be measurable. So consider something, a process like the merger of two black holes. You may ask, what if we eventually have much higher accuracy and precision in our measurements? Can we measure how the gravitation signals will decay at very late times? A simpler version of formulating this problem is, instead of having two black holes, just say, let's consider gravitational perturbations of a fixed Kerr black hole, also nonlinear perturbations of a Kerr black non, and then ask what are the late time tails. So you post some data for the Einstein vacuum equations on a hyperboloidal slice here, and you ask, what can I measure at late times when my gravitational wave detector lives on future infinity? And this is indeed known by now in the linear setting. And it's not goes by the name of Price's law. So the theorem is as follows: given smooth, compact, supported data along your initial hyperboloid, then RPC4, this is the relevant Newman-Penrose along future infinity, will decay like u to the -6 generically. This was originally conjectured in work by Price in the 70s and has recently been proved by Ma and Zhang. But again, another motivation for studying this question is that the late time tails along future infinity are intimately connected to the late time tails along the event horizon, which in turn are extremely important for understanding the strong cosmic censorship in the interior. Because Penrose's blue shift instability in the interior is counteracted by decay in the exterior. So you need to understand exactly how things decay in the exterior. So this is just another reason for why one might want to study this. Yeah.
In the second sentence of it, you said we should consider like a necessarily a nonlinear perturbation around the curve.
Yeah, so I mean, this theorem is for linear things, for linearized gravity around the curve, but you can also make statements. I'll get to that in a slide.
But these effects would like still be visible for like linear perturbations, or is this necessary that
No, these effects are visible for linear perturbations. Here, it's again, we don't look at linearized gravity on Minkowski, but on curve. So
Right.
again, strong Huygens principle fails.
option?
But of course, this theorem assumes compactly supported data, and I just told you that maybe you would want to assume different things on initial data. And it turns out that this exponent here, if I write RPC4, decays like u to the minus p at late times, this depends very delicately on what you assume on initial data. And I wrote a little dictionary together with Dejan Gajic on this, on what is known. The theorem that I just presented to you is if you have compactly supported data or for linearized gravity, then at late times you will get that RPC4 decays like u to the minus 6. If you have data that are not compactly supported anymore, but still satisfy peeling, then you will get 1 power slower at late times. But now if you have data that are informed by these constructions in the infinite past, you will get much slower decay. So for instance, if you have data that would be informed by a parabolic scattering event in the infinite past, then you would see that C naught decays like r to the minus 14 over 3, which in turn gives a late time decay of u to the minus 11 thirds. It's like 3.7. I also wrote graviton scattering here. I'll return to this later. So this is basically when you have compactly supported ingoing gravitational perturbations into your space. This is what I call graviton scattering. Okay, and for those of you that are quite attentive, you may be a little bit confused. So if you compare peeling data and hyperbolic scattering, for instance, there is a discrepancy in 2 powers at late times, even though initial data, you have only a difference in 1 powers in the decay of C naught. And the reason for that is that actually the decay depends on the limiting behavior of the quantity r squared dv r to the 5 C naught, which doesn't see this r to the minus 5 term here. If I multiply with this with r to the 5, then the v derivative will kill this, and I will see this coefficient. So this explains the difference of 2 powers here. And so going back to your question now, it turns out that if you have very irregular data, then this quantity, this is the Newman-Penrose charge, which is conserved for initial data that satisfy peeling. If you have initial data that don't satisfy peeling, this quantity will blow up. But this blow up is still conserved, right? So if you weight the limit of this quantity by the decay rate with which it blows up, or the growth rate with which it blows up, and this blow up rate will be conserved. And this is a much more robust conservation property than the regular peeling.
You mean there's some quantity that blows up, but if you rescale it with R, there's some conserved quantity you can
Yeah.
extract.
And this is the important point, this is expected to be very robust. So going back to your question now, you can study the same problem for nonlinear gravitational perturbations, so for solutions of the Einstein vacuum equations around curve. And then, okay, there is no proof yet, but there are a lot of expectations based on very recent work by Luke and O, which say that actually in the nonlinear regime, the decay will be 1 power slower for compact supported data. But in all other settings, the decay will be as in the linear theory. So actually in the case of peeling initial data, you will have a competition between linear and nonlinear terms. They are of the same order. But in the case of these conformally irregular data that violate peeling, then the linear effects will always dominate. And this is precisely because of the robust conservation of the blow-up of the Newman-Penrose charges. But that's a different story. I just wanted to mention that. So anyways, I'm saying that if you have initial data that are actually informed by stuff happening in the infinite past, as opposed to saying you just start at some finite time, then you get drastically different decay rates at late times, which are in principle measurable. Now, going back to your point, I'm well aware that matter doesn't start existing in the infinite past. And also we don't measure things at actual future infinity, we also don't measure things as time tends to infinity. All these are scales that just delicately depend on the precise comparisons between, well, the different scales in the problem that we look at. But I'm claiming that even when you look at, let's say, numerical simulations, where you pose initial data at some finite time with compactly supported gravitational radiation, you should see these slow tails as transient effects. So imagine you have a simulation where you have two masses that are very far away from each other and have they spiral towards each other, and they have eccentricity very close to one. So they are close to parabolic orbits and very far away from each other. Then you should be able to prove that in certain norms, these initial data are close to the actual initial data that would be induced by the evolution of actual parabolic orbits coming from all the way from the infinite past. And then just by Cauchy stability, you should see that there should be an intermediate regimes where both data produce comparable results. So what you should expect, even in such a numerical setup, is that there is an intermediate time regime where you see u to the minus 11/3 decay, and then at late times, because the data are compactly supported, you see a u to the minus 6 decay, or in the nonlinear setting, u to the minus 5 decay. Okay, but this is speculation. There is a recent paper by Ma and others where they actually see an intermediate decay rate of 3.8, which is quite close to this 11/3. But I'm just putting it out there that these things are in principle measurable. I don't know what the in principle means.
Sorry, did the matter just stop existing at some point? Does it violate the conservation strategy?
Well, from the dynamical point of view, you just put, you can, in numerics, you can just put your matter here, and then you say gravitational radiation is 0 towards future infinity, and then you can solve it using constraint damping. There is, okay. So this is just to say all these questions that at first may seem quite conceptual really matter for measuring things. Yeah.
So these parts of the tail, these correspond to like different entries in your dictionary that you showed us previously?
Yeah. So eventually, because here I have compactly supported data, eventually I will see the fast decay predicted by. Okay, but the question is, when do I see this? I might see this way too late for my observers to see them. And there is an intermediate regime where I see the decay coming from that you would see if you had data at infinity, where I have slower decay. Okay, but this is a little tricky because I'm appealing to asymptotic Cauchy stability and
So the entries in the dictionary that you showed us, they were not like disjoint. It was not like either one or the other. It was like they were valid in different scales and different like time regimes.
Exactly. So these are all mathematical things where in here, in the case of parabolic scattering, I really start with data at infinity, at past infinity, but numerically you can't do that. I'm just saying, even numerically, when you start with data at a finite time where you generally are compact supported, but we know by this expectations we will see fast decay at very late times, but then by some Cauchy stability arguments, you can expect that there is an intermediate regime where these data will look quite similar to the data coming all the way from the infinite past. And then you will see an intermediate regime where it will look like parabolic scattering.
What are the norms you use on the data?
Well, that's I mean, a lot of servlet norms of many derivatives of the different quantities relevant for the different curvature quantities. Okay. Questions, other questions so far? If not, then I'll use the second half of this talk to just tell you a little bit more about the more mathematical results involved in this, and I'll give you some idea of how you prove the various things.
If you're going to move away from the conceptual stuff, maybe I'll ask a question now then. So I mean, you seem to be saying that in some epistemic sense, it's better if we impose data, as far back as possible rather than compactly supported in the middle of space-time.
Yeah.
And I don't understand your reasoning there, Because to me, compactly supported data in the middle of space-time is just an idealization of an isolated system. What's wrong with that?
Okay, so you can work with compactly supported data at well, let me go to this picture. So you can work basically with the setting, but then okay, you have various scale parameters in your problem. You idealize your system by thinking that you live at non-infinity and that we have lambda equals 0 and so on. But you also have another scale where you say at some time, let's say t equals minus 100, my matter starts radiating. And all your results will now depend on exactly this time that you chose where your matter starts radiating. So this is actually quite comparable. So we don't measure things at non-infinity, we measure things at some finite radius.
But that's true for any dissipated process. And we don't say, if I want to solve for a spring in a viscous fluid, I need to go to the infinite past. It depends on the time you choose to start stuff. I don't see why this is any different.
So the point is, let me stay with this. In actuality, our decay rates here, we don't measure at infinite radius, we measure them at finite radius.
Mm-hmm.
Now, if you solve this problem Price's law, here, you will see that at finite radius, you actually get a different decay rate. And the other, because here there is not just the assumption of what, so at a finite radius, you will get a different decay rate here. And in order to not make your results dependent on what radius you work at, you put the radius at infinity. So here you introduce a large scale to your problem. If you now introduce some artificial time where your system suddenly starts radiating, then you also either need to keep track very precisely on the relevance of this time parameter that you chose in all of your estimates, which people typically don't do, or you send this time parameter to infinity. And so I'm sending this time parameter to infinity, and I'm telling you that if you do that, actually your late-time asymptotics changed quite a lot. In particular, this tells you that if you work with compactly supported data and kept track of the time parameter where you started your system, where you started the generation of radiation in your system, then you would also see some non-uniformity in this time parameter that is only removed if you set this time parameter to infinity. So it's exactly the same thing as in all the other setups of asymptotic flat.
Can I interpret whatever that's been done as radiation? Like you wanted to interpret something as radiation, and that can only be done asymptotically.
So what is the question?
But like on the Cauchy slides, you don't know the data you specify being radiation or not.
Well, I just call everything radiation.
I see.
That is not in C4.
Yeah, that can only be done asymptotically.
You can use initial condition, that's in finite time slide. You don't have to.
I just call that gravitational.
Okay.
This wants to send it. Awesome.
Is there an analog of any of this in electromagnetic waves? Or this is all purely the nonlinear gravity working here?
Electromagnetic waves on curved backgrounds, yes. Electromagnetic waves on Minkowski, no.
Minkowski is what I was thinking of. So there is, I mean, we have the complete solution there, right? But of course, we never talk about what is coming in from past infinity. I was just wondering, are there additional initial condition related uncertainties there?
You have peeling in electromagnetism as well for the field strength comparisons. Does that also get violated?
So I told you that peeling holds for linearized gravity around Minkowski. Linearized gravity around Minkowski is basically like
Yes,
electromagnetism.
I see.
Okay, so peeling holds in electromagnetism. That's that. If you introduce now a curvature to your spacetime, then peeling will fail in just the same way it does here. So that is the story. Okay.
All right, I'm still a bit confused. When you have matter, you would presumably have Coulombic gravitational field outside. And how do you get a compactly supported data?
Okay, so the let's say I'm interested in the L greater than. I look at the non-spherical symmetric part of my solutions. Okay. So I always have that 1 over R cubed. The ADM term, I always have that.
Okay,
So I call gravitational radiation. So C0 and C4, they are both always supported on angular modes greater or equal than 2. They're quadrupolar things, and this is what I care about. And they don't see Coulombic. I mean, they are relevant, they are influenced by Coulombic interactions, but
You have 15 minutes to prove everything you've said.
sorry.
Where do all these powers come from?
Okay, so I'll tell you. I'll be going a little quicker through some of these slides. So okay, I'll quickly mention the first problem that I studied in my PhD. So the first question that I asked is, if you have scattering data in the instant past, can you actually break peeling to the future? And the answer is yes, you can construct counterexamples. So what I looked is I studied the Einstein equation in spherical symmetry, and then in order to counteract Birkhoff's theorem, you of course need to introduce matter, introduce the scalar field, and then okay, you get a system of, you can rewrite the Einstein equations as a system of semi-linear partial differential equations. And I'll present the simpler theorem here. So the theorem is as follows. Look at spacetimes that are exactly Minkowski, close to past time like infinity, and then have a compactly supported scalar bump of radiation coming into the spacetime. The theorem is that generically, R phi towards future infinity will have an expansion that features a logarithmic term at order r to the minus 2 log r. This is the theorem.
You're looking at scalar radiation. rather
Scalar
than-
radiation, because it's the spherically symmetric, there is no genuine gravitational radiation. Yeah, sure. But this is just a little warm-up thing. And in fact, so these are dynamical constructions of spacetimes with a non-smooth line infinity. I claim that it's actually incredibly difficult to try to dynamically construct spacetimes with a smooth line infinity without cheating. But that's besides the point here. And right, so is it worth talking? So okay, let me maybe say roughly, okay, you need to do, in order to prove this theorem, you need to do two things. Firstly, you need to show, well, you pose data in infinity here. That's not a usual initial value problem. So what you need to do is you need to construct a sequence of solutions, all with data at some finite time. And then you push this finite time to past infinity. And then you show that the sequence that you constructed converges in some function spaces. That's the first part. The second part is computing the asymptotics of the arising solution. And here, basically, what is easy is to say, well, I can integrate my field equations to understand the asymptotics along this null cone. And now that I have these asymptotics along the null cone, I need to understand the asymptotics towards future on infinity. And I'll very schematically tell you now how that works. Let's assume we have some decay along this null cone. This is the relevant decay for my setting here. That R phi is like Q times U to the minus 1. Then in spherical symmetry, I can exploit that two derivatives, the wave equation, the U dv R phi naught. I'm now looking at the linearized problem on Schwarzschild. Sorry. The right-hand side goes like R phi naught over R cubed. Remember that in Minkowski, the right-hand side is 0 because this is a manifestation of Ström-Huygens principle. But now you still have a fast decaying right-hand side. And the relevance of this R cubed here is that I've integrated this equation twice. I have to integrate R cubed twice, which will give me 1 over R, which still decays. So I can just integrate this equation twice and improve everything that I start with. So this looks as follows. Well, I have some standard energy estimates that tell me that R phi is bounded by square root of R. I plug this into the equation, integrate in U, get that dv R phi is bounded by R to the minus 3/2. And I integrate this from the initial cone and get that R phi minus the initial value of R phi is bounded by U to the minus 1/2. When using that R is like U on the initial cone. And so you can see I now improved my initial estimate that says that R phi is bounded by R to the 1/2 to bounding R phi against U to the minus 1/2. So I improved by 1 power. So this is, I'm really just using that 1 over R cubed integrated twice. I still have a room of 1 power there. So I can eventually say that R phi will decay exactly like it does on initial data, plus partially decaying terms. And I can plug now this asymptotic estimate into the equation one final time. So I plug in this Q over U, into this equation. And okay, now I need to solve this integral. R, remember R is always like V minus U. And if I solve this integral, then this is partial fractions integral, I'll get a logarithmic term here. So there are easy ways to obtain whatever asymptotics you want to prove in spherical symmetry because you have this 1/r cubed weight. But this 1/r cubed weight is entirely special to spherical symmetry. May look like it at first, because, well, in general, the wave equation has the Laplacian, which comes with a 1/r squared weight, which you can't just integrate twice. So, and now gravitational radiation is something that happens on higher angular mode, so you may be annoyed and say, what am I supposed to do now? But now we remember this strong Huygens principle in Minkowski. So in Minkowski, we could commute R squared with R squared dV a number of times to get an exact conservation law. It turns out in Schwarzschild, we can commute with a rescaled R squared dV vector field a bunch of times to get a right-hand side that still has, so here we have R to the minus 2L, here we have R to the minus 2L minus 3, so 3 power small. Here we only have 2 power small, but 1 fewer of these weighted derivatives. So it's also really 3 power small. And so the claim is that you're still good. You can still just integrate this equation now L plus 2 times to iteratively improve all your estimates. And the result is that for spherical waves, you will then get for every single L mode a logarithmic term at order log R over R squared. Forget this L minus 1 factor here. Another interesting thing that you can prove in this setting by the same methods is that you can prove antipodal matching for the scalar field. So if you look at the limit of the radiation field towards space-like infinity along path infinity, so this limit, and the limit of the radiation field along future infinity towards space-like infinity, okay, many words, you look at these two limits, they are antipodally matched. So each L mode is matched to the other limit by a factor of -1 to the L. And this, in fact, is enough to prove antipodal matching for the Einstein vacuum equations. I just wanted to mention it here already. And now that's all for scalar waves. And now, yeah.
Is it regular term, like the log R term? Does that cause any problems? On like, so you said that makes like Scry irregular, but does it like, for example, like Scry is no longer geometrically complete or something? Or it's just like
It's not smooth.
Yeah.
You mean that along the generators along Scry, but they are geodesically complete? I mean, I would think that they are still geodesically complete.
I guess I'm asking, is there like any other from like if you get like non-smoothness, is there any other?
Well, the non-smoothness of Scry plus really concerns the transversal character. So Scry plus as an individual set, that's fine, but attaching it to your space-time, that's not fine. So all the transversal components, they are not C2. But I can tell you specific consequences of that. Okay, so I want to use the last few minutes to just tell you a little bit more about where the numbers come from. I'll quickly tell you what Walker and Will did. Okay, you do post-Minkowskian multiple expansions. The general expression for the metric for linearized gravity around Minkowski for outgoing solutions looks like this. From this, you can compute C0 and C4, and you see that C0 and C4 are functionally dependent on some pre-functions of U. And now post-Newtonian theory tells you that these free functions of U are in fact just the Newtonian multiple moments, Newtonian mass multiple and current multiple moments. So ILM of U is the mass multiple moment, where rho is the mass density of the system. Going through this very quickly, because and this is like electromagnetism really. And now all you need to ask is, what are these multiple moments in post-Newtonian theory? In Newtonian theory for the Kepler problem? And well, we recall from physics 1 that for hyperbolic orbits, the relative distance of the masses scales like t plus log t. So the mass multiple moments will go like u to the L plus u to the L minus 1 log u. And this in turn means that C0 will go like r to the minus 3 and C4 will go like r to the minus 4. And for parabolic scattering, the relative distance goes like t to the 2/3. So you get slightly different rays towards past and infinity of C0 and C4. Okay, so that was all for the generation problem. Now, I want to talk just a tiny little bit about linearized gravity around Schwarzschild. So we now know what to assume on this null cone, and we want to propagate the radiation all the way towards future non-infinity. And we do this for the system because we wouldn't see anything interesting in Minkowski. We look at linearized gravity around Schwarzschild, having in mind that ultimately I want to show you results for the Einstein-Vacuum equations. And so the procedure of linearization here is that we take the Schwarzschild metric in a double null gauge, consider one parameter family solutions also in a double null gauge that all solve the Einstein equations and linearize in our parameter. This gives this system of equations for the Einstein, for the different components. And then it was proved by the Helmholtz-Holtzsky and Laniansky that you have linear stability for this system. And okay, in view of the time that I've left, I just want to say very quickly that the main insight they had is that on the one hand, and this has been known by physicists for a long time, that C0 and C4, which is why I'm talking about that so much, both of them are gauge invariant and satisfy decoupled wave equations called the Tarkovsky equation. However, these Tarkovsky equations are mathematically hard to deal with because they have first order terms. And all this is the crucial insight. You can remove these first order terms by applying certain higher order weighted derivatives to C0 and C4 respectively. And then these new quantities will satisfy the Reggie-Wheeler equation, which is a wave equation with a potential, which we know how to deal with by a lot of mathematical work. And then you can, once you understand these Reggie-Wheeler quantities, you can get back to the rest of the system by integration and considering gauge issues a little more closely. And this general philosophy has since been upgraded to prove the full nonlinear stability of both Schwarzschild and small a Kerr. What's interesting for me here is that linearized gravity has a part that is just a wave equation, so I can apply my previous methods to compute asymptotics just as before. So now I can say, well, first of all, I need to prove that if I pose any scattering data here, then I have a solution. This is joint work with Hamid Massoud from Princeton. So if you pose data here and here, then you have a unique solution to the system of linearized gravity, where the data will consist of the News function here, the ingoing shear here, and some transversal derivative of C4 somewhere along this cone. This is a bit weird. I'm disregarding issues of gauge here because in reality, the data contain much more information, but you can remove all that information by gauge transformation. For instance, by choosing the sphere here to be round. So in general, you can choose that sphere to be anything, but you can always add a gauge transformation so that that sphere becomes round. So the Gaussian curvature is exactly one asymptotically. This is essentially bonding normalization. Okay, and now assumptions to place on the scattering data. Like I said, for hyperbolic n-body scattering, I say that C0 goes like r⁻3, C4 goes like r⁻4. For parabolic scattering, I say that C0 goes like r⁻11�3, and C4 also goes like r⁻11�3. But both of these rates are motivated by post-Newtonian heuristics. If you don't like that, you can consider graviton scattering, where you have rigorous results instead. If you say your spacetime is exactly Minkowski or exactly Schwarzschild, close to past time at infinity, then you can prove that there is a null cone, and then you have a compactly supported gravitational radiation bump going into the spacetime. Then you can prove that there is a null cone beyond our gravitational radiation going to the spacetime, where you have the following rays, which are essentially the same as for massive n-body hyperbolic scattering. Okay, and the result now is here. It looks simple like this. So you can find the complete asymptotic description of the resulting solutions. So if you have scattering data describing the exterior of hyperbolic n-body scattering, as on the previous slide, then you can prove that C0 will have a term that is like u squared over r to the 5 plus a 1 over r to the 4 term. And this, going back to your question before, this r to the 4 term is a constant. So the limit r to the 4 C0 long to infinity does not depend on u. And this is actually true for all angular modes. The original Newman-Penrose charges are only conserved for L equals 2, if spacetimes peel. If your spacetimes don't peel, they are all conserved. All L modes. So an infinite number of conservation laws here.
But it's still linear here.
Exactly, exactly. But everything that I'm writing here, I expect to be true for the nonlinear theory, which I'll tell you in 2 minutes. So you can also obtain a complete description of the decay rates along scribe class as u tends to minus infinity, and you can prove antipodal matching so that the two memories match antipodally. Here, chi hat bar and chi hat are the incoming and outgoing shear, so the news functions along both infinities. So let me just put it in words instead. So starting from a hyperbolic n-body scattering data set, we obtain asymptotics towards space like infinity, where psi naught goes like r to the minus 3, and towards visual infinity, where psi naught goes like r to the minus 4. And this is weaker than the typical assumptions people have placed on Cauchy data. So for instance, this is weaker than the assumption that was posed by Kuzulo and Kleinemann in their work on the stability of Minkowski spacetime. And you can prove antipodal matching for the news as a consequence of antipodal matching for scalar waves. Now, downsides here is that I always just talk about fixed angular modes. And if you keep track of the error terms that I'm always writing as dot dots, they will go like L to the L. So even for smooth initial data, this is not summable. And I haven't told you anything about how to treat nonlinearities. So we require something new, because if you look at the actual Einstein vacuum equation, this is the Reggie-Wheeler equation, the Einstein vacuum equations, there are many, many nonlinear terms.
Like the Reggie-Wheeler is the simple one, right?
Yeah, yeah. Really so only this term corresponds, these two terms correspond to the linear part in Schwarzschild. All the others are nonlinear. So that sucks. So we need something quite robust. And this quite robust is the final theorem of this talk. So in recent work with Ishwan Kadar from Princeton, we proved that for a very general class of perturbations of the linear wave equation on Minkowski spacetime, which in particular includes equations like this, if you have a polyhomogeneous expansion here and here, then you'll have a polyhomogeneous expansion everywhere. Polyhomogeneity, recall, that means that I have expansions into r to the minus p for some non-integer powers p, potentially non-integer, and log n r for some integer powers n. And so we just proved generally that you have expansions, and then a posteriori, you can wonder what the coefficients in these expansions are. And you can do this by projecting onto L modes. But you already know that you have the expansion, so you don't need to worry anymore whether you can sum your estimates. So this is the neat little trick in this theorem. The theorem has a surprising application to the interior of extreme horizon Nord Stream black holes, which is funny, but because there is a conformal isometry between the space-like infinity of negative mass extreme horizon Nord Stream and the interior of extreme horizon Nord Stream. Anyways, this theorem basically allows us to treat most things that we want to treat. And okay, I don't have time for the proof, but I just want to summarize. This is now ongoing work for the Einstein vacuum equations. We can't apply the Einstein vacuum equations are slightly more than system of wave equations. There are many other things in it, so we can't directly apply this theorem. But basically, we strongly expect that everything that I said before still holds. So I only wrote down those things in the previous linearized theorem that I expect to be robust for the nonlinear setting. So in particular, I expect that psi naught will decay like r to the minus 3 towards space-like infinity, and like r to the minus 4 towards fusion infinity, and that will be conserved for all angular modes. Now there is one little catch here. For hyperbolic orbits or graviton scattering, it turns out that there is a competition between linear and nonlinear terms. So I can tell you about the constants. I just can tell you that that is the rate, but I don't know which is the dominant constant. Whereas for parabolic orbits, where everything decays 2/3 faster, the linear term is completely dominant. And in particular, you can prove that antipodal matching for the news along space-like infinity holds, because this is part of the previous theorem with Ishwan-Kadar, because it holds for a large class of nonlinear scalar waves. So that's the end of this talk. Sorry for slightly overrunning. I included 2 pictures with the global expectations of decay rates that I painted in the case of graviton scattering. And I wrote, thank you for your attention. So thank you for your attention.
We can have a couple of questions over time.
I thought, quick, just conceptual question, you've mentioned observing a couple of times. How do you observe any of this, or what, are you looking at ring downs or binary black hole mergers and thinking about how the gravitational waves decay over time?
Yeah.
How can we really observe these in the physical universe?
So going back to basically exactly what you said. So there will be the usual ring down with the oscillations that we know so well, and then if our accuracy was much higher, then we would expect to see some kind of polynomial decay. The black hole settles down. Let's say we have one remaining Kerr black hole, and then by Price's law, we expect that at very late times there will be some polynomial decay. And so much later.
How accurate do you need to be, or which strain do you need with a gravitational wave detector in order to detect these different regimes?
This is not my expertise. I'm putting it out there because I think that this is in principle something that one might wonder about. I know nothing about I would expect quite a lot higher. I talked to numericists and some people working on LISA about this, and they said, well, we have no idea. There are some recent papers that claim that you may be able to measure these tails at late times, but they would require a lot higher accuracy. Then again, 50 years ago, we didn't expect that we would be able to measure what we're measuring today. But this, I do maths. I can't really give you that.
That's not an excuse.
I'm very happy. I'm talking to, like, I'm not qualified for it, right? I'm talking to people because I want to know the answer, but like, this is not my. I think from what I remember, 10 to the like 5 more orders of magnitude at least.
Like 10 to the minus 26.
Yeah. I think I've been told something like, but like I have no means to check that.
Let's see if someone else has a question. It's quite a few.
Oh, yeah.
Thanks for the nice talk. You mentioned you had a discussion on conserved charges.
Yeah.
I was just wondering what happens to the Bondi mass. Like, are you saying it is like, let's say you have this graviton scattering experiment. What happens to Bondi mass on strike plus? Is it enhanced, or like for a single, like if you were to pose initial data that were really compactly supported on some time slice, nothing from past null infinity. You get some, when it scatters off, you will see some amount of radiation on infinity. Are you saying you'll measure more or less?
I don't understand what you mean by more.
So you have two
But
scenarios.
this
Right. In this scenario, would
Yeah.
you, so if you had the same energy in the two wave packets of the gravitons, this is scenario 1. Scenario 2, scenario 0 is the case where you had the same energy on some Cauchy slice, right, which is compactly supported, and you're not getting, you said 0 asymptotics. So what do you measure on Sky Plus?
So I measure in this setting, I measure that the Bondi mass will decay much slower to 0 compared to the setting of compact supported data.
So you will just at some, let's say at some finite time, you will measure more mass, or you'll see the decay to be slower, right? That's what you said.
Yeah,
Okay.
the decay is slower. There is also the constant in front of the
Right.
decay term, so I don't know if I will at any finite time. But okay, at very, very late times, there will be more mass in the system. Yeah.
Okay, let's go over time. Any questions for discussion? That's great.